that after going through this module, you should be able to use group theory to predict the normal modes of vibration of polyatomic molecules and also determine their IR and Raman activity. So, a brief introduction. It is relatively easy to predict the number of vibrational modes of a triatomic molecule. Picture the motions of atoms using arrows and predict the IR and Raman activity as we have done for water and carbon dioxide molecule. In the case of the former, there should be a change in the dipole moment during the vibration. We've seen that infrared activity depends upon a change in the dipole moment during a vibration, and in the case of Raman spectroscopy, there should be a change in the polarizability. But when you have larger molecules, it is not so simple. But here group theory comes to our help, and it proves useful in determining the number of normal modes, their symmetries and IR and Raman activities. So briefly we will talk about what are normal modes of vibration. Consider the carbon dioxide molecule and picture the behavior of the arrows which are shown in figure under the various operations of the molecular point group, which is d infinity h, because this molecule has a center of symmetry, and this is mentioned in table 1. So, in figure we have given the normal modes of carbon dioxide. One is the symmetric stretch, the other is the antisymmetric or asymmetric stretch, and then you have a pair of degenerate modes which are the bending modes. And the arrows show the kind of motion that is present in each one of these modes. And as we said before, the character table of d infinity h point group applies to this molecule. And what are the different operations? One is E, the identity operation, that C infinity axis means that you can rotate by any angle along the bond axis and the molecule looks the same, and there are an infinite number of vertical planes passing through all these C infinity axes. There is a center of symmetry which we call I. There is an improper rotation. Again, you rotate the molecule through any angle and then you reflect it in a plane perpendicular to the axis. This is S infinity, and there is also an infinite number of C2 axes. So, we will first look at the symmetric stretch vibration. The arrows display the same appearance under the various operations of the point group. For example, if you do an E operation, nothing happens. When you do a C infinity operation, nothing happens. When you do I, also the two oxygens exchange positions and the two arrows also exchange positions, the appearance remains the same. So, the character is 1 for this also, the character is 1 for all the operations, and that means that it transforms as sigma G plus, the most symmetric representation of the d infinity h point group. For the antisymmetric stretch, the arrows present the same appearance under E, C infinity and sigma V, but they change direction under the remaining 3 operations. Therefore, it transforms as sigma u plus, as you can see from the character table. It is a u vibration because the arrows, they change sign when you reflect or you perform an inversion operation to the carbon atom. It can also be shown that the doubly degenerate bending modes, it is a little more difficult to show there, but you can show that they transform as pi u. So, we may define the normal modes as independent harmonic vibrations which leave the center of the mass unmoved. Why? Because if the center of mass also moves, then there is also a translation motion, but we are talking only about vibrations. They involve all atoms moving in phase, coherent motion, all the atoms are moving at the same time in phase. That means they execute a vibration at the same time, they reach the maximum phase at the same time, the minimum phase and the equilibrium position at the same time. They also transform as an irreducible representation of the molecular point group. Normal modes of some other linear molecules, they are shown in table. You can see that there is an N2O molecule which is not like carbon dioxide because it does not have a center of symmetry, it is NNO. The first mode of vibration similarly is the symmetric stretch mode, and here there is no center of inversion, so there is no G or U notation, it is a sigma plus vibration. The bending mode is again doubly degenerate. We have shown one of the motions, it is a pi motion, and the other one is again sigma plus the antisymmetric stretch. Similarly, HCN also does not have a center of symmetry, and similarly you have sigma plus, pi and sigma plus, and acetylene is a little more complicated because there are 4 atoms. So there are 4n minus 5, it is a linear molecule. There are 7 modes of vibration, out of which there are 2 pairs of degenerate bending motions. The stretching motions are sigma g plus, the symmetric ones are sigma g plus, and the other ones are sigma u plus, and the bending modes are, one is pi g because it is it is symmetric with respect to inversion, and the other one is pi u. We now consider a bent triatomic molecule like water. We want to work out how to find out what are its modes of vibration. We had done it arbitrarily last time because we were comparing it with carbon dioxide. Now we want to work out the procedure to find out what are the modes of vibration of a molecule like water. It belongs to the C2V point group. The C2V character table we have shown here, and you can see it in any book on group theory. Similar to carbon dioxide, in water also there is a symmetric stretch mode, there is a bending mode and an anti-symmetric stretch mode, as we have pictured here. In the symmetric stretch mode, we had already explained that that is called nu1 because it has A1 symmetry. Nu2 is the bending mode. It is also of A1 symmetry, but it is at a lower frequency, so it is labeled nu2, and nu3 is the anti-symmetric stretching mode. Since water molecule is non-linear, there are only 3n minus 6, which is equal to 3 modes of vibration. For it, the Cartesian coordinate system and the symmetry elements are as displayed here. By convention, the most important axis is called the z-axis. Here it is the C2 axis passing through oxygen and bisecting the angle between the 2 hydrogens. Then the yz is the plane of the molecule, so y-axis is defined so that it is the yz defines the plane of the molecule and x is perpendicular to the plane of the molecule. So these are the 4 symmetry elements. One is E, one is C2, which we have shown here, sigma v xz is shown here, and sigma v yz is also shown here. You will find that the first 2 vibrations, that is the symmetric stretch mode and the bending motion, they transform as A1, and the third one, which is the anti-symmetric stretch, that transforms as B2. For example, the result of a C2 operation on nu2 and nu3 is as we have shown here. For nu2, when a C2 operation is performed, nu2 is the bending mode, the appearance remains the same, but if the same operation is performed on the anti-symmetric stretching mode, what happens, all the arrows, they have reverse direction. So nu3 has become minus nu3, so the character for nu3 for C2 is minus 1, and for nu2 it is plus 1 because it did not change any direction. Now we will obtain the 3n dimensional representation of water molecule as shown in figure and subtract the translations. They are 3 in number and rotations which are also 3 because it is a non-linear molecule to obtain the 3 vibrational modes. So this is the 3n dimensional representation of water molecule which is shown in figure. What have we shown? We have shown that each atom is labeled with 3 Cartesian axes, and each one of them has an x, y, z. There are 2 on the 2 hydrogen atoms and 1 is on the oxygen atom, and 3 into 3 is 9. So it is a 9-dimensional representation for the water molecule. So only those atoms that are unshifted in an operation contribute to the character. The character per unshifted atom is 3 for E, minus 1 for C2 and plus 1 for all sigma. So in table we have shown that the normal modes of vibration are like this. For character for each mode is like this. For E, the symmetry operation, the character is 3. For C2 it is minus 1. For all sigma it is 1. And then the number of unshifted atoms under the E operation is 3 because all atoms are unshifted. Under C2, the hydrogens shift position, only the oxygen is unshifted, so the character is 1. Sigma xz, again the same thing happens, only the oxygen of the water molecule is unshifted, hydrogens exchange position, and in the plane of the molecule all 3 atoms are there, so the number of unshifted atoms is 3. We multiply the first row by the second row, so we get 9, minus 1, 1 and 3, and out of this we subtract translation and rotation to get the vibration. How have we done this? Multiplication of the number of unshifted atoms by the character of the corresponding symmetry operation gives the 3n dimensional representation. Here it is 9. The characters for translation can be obtained by summing together the characters of x, y and z from the character table, because the translation motion can be the motion of the center of mass in the x direction, y direction or the z direction, and for rotations you can obtain it by summing together rx, ry and rz, which signify rotation along the x axis, the y axis and the z axis. Subtraction gives the reducible representation for vibrations. So when you use the great orthogonality theorem to find out what are the irreducible representations, we get 2a1 plus b2, as we already knew because we have already done this in an arbitrary way before. So now we come to the selection rules for infrared activity first. It can be seen that the dipole moment of the molecule changes during each mode of vibration of water, so that all modes of vibration of water are IR active. Here we can do it by inspection alone, but let us see how group theory helps in this respect, because we ultimately want to use group theory for more complicated molecules where it is not so obvious. The intensity of a vibrational transition is proportional to the square of the transition dipole moment, which I am giving a symbol as MLM. It is a vector quantity, but we are taking its modulus. So we have a bracket consisting of straight lines, which can be expanded into its components in the 3 Cartesian directions. That is, MLM is I direction, which is the x unit vector in the x direction, into mu xlm plus j mu ylm plus k mu z lm. I, j and k are unit vectors in the x, y and z Cartesian directions. If all 3 components are 0, the transition is forbidden. Alternatively, if at least one of the components is non-zero, the transition will be allowed. Consider, for example, the mu xlm component. It is a triple integral. It involves the excited state vibrational wave function, the ground state vibrational wave function and the x component of the dipole moment operator. Double prime to V prime transition, it is given by mu xlm is equal to an integral from minus infinity to plus infinity psi V prime mu x psi v double prime dx, because we are talking about one dimension only, and psi v prime and psi v double prime are the excited and ground state vibrational wave functions respectively, and mu x is the operator for the x component of the dipole moment. So only if the product is completely symmetric will the integral survive. This integral will vanish unless the triple product transforms as or contains the totally symmetric irreducible representation of the point group of the molecule under consideration. For example, we have seen that for C2V, C3V and so on, the totally symmetric representation is A1, sigma G plus is for D infinity H, sigma plus for C infinity V and AG for C2H and similar point groups. So the totally symmetric representation, if that is contained in the integral will survive, otherwise it will vanish. So we have already seen that the selection rule for the harmonic oscillator is delta V is equal to plus minus 1, and most molecules are in the V is equal to 0 level at the room temperature because of the spacing of the vibrational energy levels, which is very large. Therefore, the most important transition is the fundamental, and which is the transition for a change in vibrational quantum number from 0 to 1. The ground state wave function is given by, you have already seen, psi 0, n0 is the normalization constant for this state, h0 is the Hermite polynomial for this, which is a function of y, and e minus y square by 2, or this is equal to n0 exponential minus alpha q square by 2, because alpha is equal to square root of mu reduced, the reduced mass multiplies by the force constant, the square root of the whole quantity divided by h cross, and y is equal to square root of alpha into q, and q is the normal coordinate. So the sign of 0, if you look at this expression for psi 0, you find whether q is positive or negative, the sign remains the same, because h0 is equal to 1 and It is therefore independent of the sign of q, which appears as its square in the expression for the wave function. It follows that psi 0 transforms as the totally symmetric irreducible representation of the relevant point group. The excited state wave function similarly is psi 1, and this is equal to n1 into h1 as a function of y e raised to the power of minus y square by 2, and this can be written as n1 into 2 into square root of alpha q, because h1 as a function of y is equal to 2 y, and that is why, since y is equal to square root of alpha into q, we have written this, and exponential minus alpha q square by 2. Now, because you have this q term, you have square root of alpha into q in this expression. Psi 1 has the same symmetry as the normal coordinate q1, that is psi 1 transforms as the same symmetry as the normal mode. We may now summarize in table ground and excited state wave functions for the 3 modes. Symmetries of ground and excited state vibrational states for water. In the mode, first mode, which is the symmetric stretch, the normal mode is A1, so psi 0 is also A1, and psi 1 is also A1 because it transforms as the irreducible representation of the normal mode. Similarly, in second mode it is bending, it is again A1 for both. But in the antisymmetric stretch, since the normal mode transforms as B2, psi 0 has A1 symmetry, but psi 1 has B2 symmetry. This analysis also applies to other symmetrical bent molecules, triatomic molecules of the type AB2, such as H2S, SO2, NO2, all of which have the same shape as water molecule. Now we consider the x component of the dipole moment, because this is the third term in the integral. It is given by mu x is equal to summation of qi, the charge on the ith particle, into xi, where qi is the charge on the ith species, it therefore behaves like x. From table 3 we can see that this transforms as b1. Therefore, the components of y transform in C2v as mu x is equal to b1, mu y is equal to b2, and mu z is equal to a1. We now return to the triple product in equation. We know that the ground state wave function is always totally symmetric, and so the product depends on the other two quantities. We also know that the direct product of any symmetry species with itself gives the totally symmetric representation. If you multiply anything by itself, you always get -1 into -1 will give you +1. So, it will give you the totally symmetric representation. Therefore, the integral will be non-vanishing if any of the three components matches with the symmetry species of the normal coordinate. Both the symmetric stretch and bending modes of water transform as A1, and so Z also transforms like this. Therefore, both these modes can be excited by the Z component of the electric field of the radiation, because then you have A1 into A1 into A1 and the whole integral transforms as A1, so it is non-vanishing. Further, the antisymmetric stretching mode transforms as B2. We find that Y also transforms as B2, so this mode is also infrared active, excited by the Y component of the electric field of this electromagnetic radiation. Thus, all three modes of vibration of water are infrared active, and this we have shown using group theory, and we have not done it by inspection as we had been doing earlier. We now come to the Raman activity. The molecular property that must change for a vibration to be Raman active is the polarizability of the molecule. Unlike the dipole moment, which is a vector polarizability, we have seen as a tensor quantity, that is, it has 9 components in the x square direction, rather xx, yy, zz, xy, xz, yz, yx, zx and zy. Thus, correspondence between a normal mode and any one of these components implies that the vibration is Raman active. Now, table for C2v tells us that the three species x square, y square and z square all transform as A1, and so the symmetric stretch and bending modes are Raman active. The product yz transforms as B2, and so the antisymmetric stretch is also Raman active. Thus, all modes of vibration of water are both IR and Raman active, as we had seen by inspection alone. So, we will summarize what we have learnt in this module. Group theory helps in determining the symmetries of the normal modes of vibrations. The infrared and Raman activity is also easily determined using the group theory. And finally, for symmetrical bent triatomic molecules, all three modes are both infrared and Raman active.